Okay, yeah, I guess we'll just go ahead and get started. Um, Hello and welcome to the very first NeurotechSC podcast. Um, I'll be hosting today. My name is Alex Solis, and I'm here today with the NeurotechSC president, Rohan Pandey, and the technical and research advisor for NeurotechSC, Kate Voitiuk. How are you guys doing?
Great.
Yeah, I'm
Nice to
doing
be
great.
here.
Yeah,
Okay,
looking
cool.
forward to the first NeurotechSC podcast.
Yeah. Also, I was gonna ask too. Yeah. I guess is it? We never really came up with a name for it, did we? I guess, huh? I guess we'll just roll with the Neurotech SC podcast. I guess, right?
I feel like we could even just go with the Neurotech podcast. I don't think now there's one other podcast that we do know exists about neurotechnology, but they're named something else. I forget what they're called, but they started like a week ago. But I think we're allowed to go with just the Neurotech podcast.
Yeah. We should try to snatch up that name before before it gets taken. Yeah.
Yeah.
Okay. So I guess the first thing we wanted to cover was So in general, Neurotech SC being one of the newer clubs on campus of UCSC, and its main focus being in neurotechnology. So, in general, how exactly did Neurotech SC come about? I mean, I believe it's only been maybe 6 months old now, just about.
Actually, it's technically over a year now. In terms of when it became an official club on campus, that was fall quarter this year.
Mhm.
But it really did start last March. So last March, I had sort of been thinking about the idea of starting like a brain-computer interfaces related club on campus for a few weeks. And someone mentioned to me NeurotechX, which like at their college at UIUC. And like I was like, oh, that sounds kind of cool, whatever. And then someone else mentioned it to me from UC Davis, and then I was like, oh shit, maybe this is like a real thing. And that's when I started like really getting into creating like a NeurotechX chapter at UCSC. And then I reached out to Kate and like got a bunch of officers on board. Nothing really happened for the first few weeks. We were planning on just doing like a curriculum style kind of club, right, where we just teach neurotech related curriculum, and then we have projects every now and then. But I think it really took off when we started the main NeurotechX student competition project in when was it, August? Yeah. In August we started that the actual project, and then it really improved a lot in the next few months. I was actually really surprised by the pace at which it developed. Within the first month or two, we had like gotten a ton of hardware and set up all the teams, right? We were originally planning on having 6 teams with this additional 3D printing team, but ultimately that just got merged with the hardware team. It took off pretty quickly. We got like a ton of new members. And then I think Kate is trying to join again. All right. It improved at a surprising pace. Within the first 2 months, I think we actually had a working prototype by late September, I think. When the school year came around, that's when things started slowing down again. And then we continued making a lot of progress, but it was definitely slower during the school year. In November, we submitted it to the NeurotechX competition, and then we heard back 2 or 3 weeks later, and we found out that we had won first place in the US. So that was a really awesome kind of thing. Obviously, we didn't win like first place overall, so like we didn't get any prizes or anything. We were beat out by some Canadians, unfortunately, but it was still really impressive to see us as like a club that had just been founded like a few months prior, basically beating out like the NeurotechX clubs all across the US. Over the past quarter, right, winter quarter, we've been mainly focusing on more like deeper research and longer term thinking into like getting this into a more productionizable state, and also adding like newer, like much more effective features. So yeah, that's sort of the story of NeurotechX up till this point.
Wow.
I don't know if Kate has anything to add to that. I hope I covered most of it.
Yeah, that was a good summary. And it's from at least in terms of my perspective, it was really exciting to see Neurotech Club on campus, because that's something unique and that's something that has never been before on campus. Just
Yeah.
UCSC diving into that area in general is pretty cool, along with other UCs that are already in that space. I think it's good to establish our presence and also show our enthusiasm for what's coming in the future.
Yeah, NeurotechX is like an overall organization as well as like very new. It really only started in 2016, I think. And all of the UCs all had their like clubs founded in the past couple of years. So yeah, as a whole, the whole organization, like NeurotechX, is very new, and I think NeurotechSC is developing at a pace similar to the rest of the organization, if not faster. So that's really exciting to see.
Yeah, 100%. I have to agree as well. I was definitely very excited to see this club and discover it. I mean, the only reason I even came across it was through Rohan in general. And it was really cool to see, as a cognitive science major and computer science minor, this kind of fits in that like perfect little snug mix between the two. So it was super cool to see that. And it's honestly really, yeah, I got to say, it's very impressive to see how far NeurotechSC has come. Yeah, definitely. Yeah, so I guess jumping in a little more into that, what exactly is the major project of NeurotechSC?
Yeah, I talked a bit about the history already, so maybe Kate, you want to talk about the project and the inspiration and everything?
Sure, definitely. So our project is called Boolepathy. It's kind of a name that we came up with after the fact when we're just submitting the project. But the main idea is to use subvocalization to understand what a person's internal voice is saying and have a computer execute on those specific actions. So subvocalization is a phenomenon where a person might say something in their head without actually speaking it out loud, but their facial muscles would twitch in a way that would correlate with the speech that they would produce if they were to actually engage their vocal cords to speak. So we are placing electrodes in the area near the mouth and chin in special areas that were previously published in papers on subvocalization. And the most recent one was from MIT. I think they, Rohan, do you remember the code name?
Yeah, alter ego. It's called alter ego.
Yes.
I think it was an undergraduate or like master's paper, but yeah, it was pretty much exactly, or if not very close to what we were doing.
Yeah, and the goal is to create a silent speech interface between a person and a computer so that a person doesn't have to say commands out loud, because currently we have voice assistants that kind of fill the role of speech controlled actions that you can do on a computer, but sometimes people are shy to speak in, for example, public transport, or there's too much noise that might be happening outside, or it might be too disruptive, for example, in a library where you don't want to speak out loud, but you might want to have some convenient voice controlled features, maybe to change music or to look a word up, for example. And so I think there's a really great niche for these silent interfaces. And this is something that we're trying to build. A lot of the interfaces in literature have a very limited vocabulary. For example, they might have digits 0 through 9, and maybe some letters or some keywords like opera, but none of them can transcribe full-on sentences into actual text. So the first part of our project was to just get an interface that could classify yes or no words and be able to control certain user interface to transcribe sentences into words and text to then pass to some voice assistant that is already integrated with a lot of the computer features.
Yeah, and also a really important thing here, I think, is that like we don't know whether it's possible yet. That's like something that we're still like completely investigating. We think it should be possible, considering that some papers have like pretty huge vocabularies, but they're like still learned with a classifier, where it like learns, like the classifier learns with like pretty high accuracy whether a word is in like one of these 30 different categories, like whether a subvocalization matches one of these 30 different words. So just given that, we think it should be like there should be some kind of logical phonemic signal underlying the subvocalization, which means that we should be able to like dig into the signal and learn meaningful correlations between these like EMG muscle like signals and actual phonemes that the user is like thinking. And if we're able to do that, then we should be able to transcribe these sentences exactly as Kate mentioned.
Yeah,
Yeah.
that
Also,
sounds.
something I forgot to say was that the name Boolepathy came from Boolean. So our first deliverable project to Neurotech was to just classify yes or no to answer some questions presented in a user interface. And Boolepathy as in yes or no, and empathy is for telepathy, kind of, because it's a synthetic telepathy project. But in the future, as Rohan was saying, we would like to do full-on sentences, which hasn't been done before.
Yeah, I've got to say, it's funny you mentioned that too. I was actually thinking about the name Boolepathy, and I didn't fully realize what it was until literally, I think yesterday maybe. I was just thinking about. I was like, oh, Boolean, as in true and false. Yeah, going with the yes and no as the main project. Yeah. So I guess moving forward, you'll probably have to rename the project as you start to develop full sentences.
Exactly. It's definitely going to be renamed something like I don't know, algebrapathy, or like I don't know what, like how do you, I don't know, some group theoretical term that refers to the set of all real numbers rather than just 0 and 1. Well,
Yeah,
yeah,
definitely.
yeah.
Yeah, super cool though. Definitely super cool. So, yeah, so I guess that covers the what's coming next for Neurotech SC and going into the future of Boolepathy. Um, yeah, so I guess yeah, one thing I kind of did want to discuss as well, um, which I guess to give a little bit of background on that. Um, I think when I first told, when I first joined the club, I was talking to my parents about it, right? Um, the first thing my mom said about this was that we're developing a machine to read our thoughts, and there was that nice stigma behind it, right? And it does bring up a very valid point that I think a lot of people have behind brain computer interfaces in general. There is that type of uh, I don't know. I guess I would call it a stigma, I guess. And eventually, I'm assuming as neurotechnology seems to develop, will turn into a bit of a controversy, right? And things like Neuralink start to take wind and make a lot more progress. Um, yeah, I don't know. So, what are your guys' thoughts in general behind this stigma that'll kind of begin to grow?
I think one nice thing about neurotechnology is that we basically know that you can't read thoughts um, very clearly, at least non-invasively. With just EEG signals, you're not going to be able to, like, it's like people, there's plenty of different companies that are using EEG signals, and like no shade to them, but like there's honestly not very much you can do with just like a non-invasive EEG signal. No matter how many channels you add, whether you have like 30 channels or 60 channels, some even have like 120 channels. No matter how many you add, you're just not going to get like the kind of information that you would want if you're trying to do something uh, like reading thoughts. For that, you do need these kinds of invasive interfaces that are going to, like Neuralink that you mentioned, for example, they would have to like go into the brain and read specific parts of the brain to like pull out information. Um, there is subvocalization though, which I think like that's another kind of inspiration behind this project, because we think it's like really understudied. Um, because with that, you weren't really able to read thoughts. You're able to read subvocalizations, which are mainly produced when someone is reading something. So when they're like reading text, but you can also cause yourself, you can consciously subvocalize. Um, and that's how you would actually communicate with the system. Um, so yeah, I think it's definitely going to be a controversy eventually. But the nice thing is that we don't have to think about it for a while, because I don't think people are going to be willingly getting brain implants for at least a few decades.
Yeah, definitely. I could agree as well.
Yeah.
Yeah.
I think also going into the future, I think this would not just be a neurotech question. I think this would be a data privacy question. And how do we handle personal data, whether that's going to be potentially sent off the device and into some cloud interface that might not be completely secure, or if it might be posted publicly or intercepted publicly. So I think it's not just about recording our brain signals, whether they're invasive or just outside EEG, but also how we treat that data and how we store that data. For example, it's really cool what Apple was doing with Face ID, where they don't actually store your, or they claim that they don't store your ID in the cloud, they store it on your device, and they have that representation uh, only on your device, which I think is a bit more private than having it shared with Apple ID in the cloud. So maybe having processing of your neural signals on the device that you're carrying and not sharing them over the network, or sharing kind of a processed version of them over the network that is limited to what you specify might be a good policy. But I think since the technology is so new, I think there's a lot of opportunities in developing those standards and making sure that people comply to user privacy as much as possible. It might be something on the legislational level, perhaps, or um,
Yeah. No.
government or state.
I have to completely agree. Yeah, and I think this was definitely something I think Sahil and I started to get into a little bit when we last talked about neurotech in general. Um, yeah, I mean, can you imagine if we had that type of that full on thought reading process, and if that was able to uh, be given to the hands of data mining in general? Can you imagine the ads you'll be getting? Just off of your thoughts alone. Yeah. Um, yeah. So I think privacy is going to be one of the biggest things.
Yeah, that's sort of one of the things I've thought about. Like, if NeurotechSC does evolve into like a actual production oriented enterprise, which some people have floated the idea of, if the sub-localization project does take off, one of the sort of nefarious claims that we think like any brain computer interface company would be able to make is both is like very like it's sort of about privacy. So I'll just like lay out the idea. Um, if if we expose this data directly uh, to like ad companies and everything, um, they could potentially use it for like bad causes. Therefore, the company that produces the neurotechnology products would claim that it's best for consumer privacy to maintain a monopoly over their data. So now it's only this company that has like this gateway into everyone's brains. And I don't know. I think that's sort of a like a scary possibility. I don't think that would improve consumer privacy. And I think it's also sort of similar to the whole privacy versus like security debate that is going on right now. Yeah, just sort of a thought experiment.
I mean, what
Yeah.
idea is not to collect data at all, but then data, on the other hand, is extremely valuable and it can further the quality of algorithms and services that could be provided to people uh, going the other way. So I think it's an interesting debate of whether or not people should or should be able to choose to share their data. Probably people should be able to choose whether or not to share their data, given the information that, on the other hand, their privacy might be uh, less, but the return might be more. Again, theoretically speaking, probably everyone would want to benefit from algorithms that mine and train on lots of data, but nobody wants to give up their own data. So that might be a bit of a interesting situation. Perhaps it could be monetized in some way. For example, you can make money selling your data. I think that actually that's probably completely reasonable to be compensated for providing your data, because your data is valuable ultimately.
Yeah, and I think it's funny too because that sits in line with um, a lot of psychological research in general. I think one of the leading leading laws as far as efficacy goes is that, yeah, people do need to be properly compensated for their, their contribution. So I think, um, possibly, yeah, just going off of what you're saying, yeah, it could be um, this data coming from the brain specifically, maybe potentially these privacy laws and everything like that could possibly fit under psychological research and those specific laws that are protecting people in that case. Yeah, so that'll be really interesting. Um, Hopefully, at least. Yeah, I think going off of what Rohan was saying as well, it kind of might just turn into once we reach a certain point in neurotech development where it turns into um, a bit of an arms race where companies are trying to be that first to fully develop that thought reading device to get in order to secure claims towards that data. Yeah, and what happens to that data. So yeah, I think that could be potentially dangerous.
Yeah, and I think another downside of downside of neurotechnology is the fact that you need to do this kind of calibration for everyone. At least right now, like with our current project, we found that like if you train on one person's data, it is only really effective for the rest of their data. Um, you have to add some kind of calibration step to be able to scale from one individual's training data to the other. So that's like another interesting kind of machine learning problem that we're going to be facing in the next, I don't know, 6 months. It's not what we're focusing on right now, but it's like on the roadmap. But yeah, the fact that you need to have this kind of calibration for every single user is sort of another downside, because now you can say, oh, I have to collect your data in order to be able to provide you with these services. One flip side of that though is that, like, I don't know, this is a recent kind of paper that we covered in our paper reading group. They found that just 1 hour of exposure to a brain-computer interface causes these changes in neuroplasticity, where the brain's structure actually changes to adapt to the brain-computer interface, even if the interface wasn't calibrated for the user in the first place. So maybe that's another kind of approach that will happen. But I mean, obviously for that, there's a steeper learning curve, and you're forced to kind of struggle with it for a bit before you figure it out. Whereas if you have calibration, then it would be much easier. So that's sort of another ease of use versus like privacy kind of trade-off. Like, do you want to spend like a few days or weeks maybe learning how to use this interface and keep your data private, or do you want to trade your data for this like easy calibration that gets that gets you like a much easier introductory experience to the interface? So yeah,
I think
kind of a yeah. Go ahead, Kate.
that's a really interesting point that you're bringing on, and I'm almost imagining a future where we might have more complex user interfaces with many more input areas, and perhaps the strategy there would be for both the user and the interface itself to adapt to each other in order to integrate faster and learn faster together to be able to be more effective at computer-mediated task of some sort.
Yeah, this is sort of something that I think Kate's lab is on track to work with, right? Like direct, like neurons interface, like biological neurons interfacing directly with artificial neurons, and somehow having like a backprop that propagates over the boundary. Yeah, I don't know, Kate, if you want to talk about that, that would be super interesting as well.
Yeah, I could touch on it a little bit, but I don't want to steal too much of the time on lab stuff. But essentially, something that I'm really excited about working on is trying to see, firstly, trying to understand how the brain works using in vitro biological models, namely organoids. And organoids are just 3D tissue, specifically in our lab, we're growing cortical tissue derived from stem cells. So we have some stem cells in the lab and we add factors to them, just small molecules that eventually turn these cells that are dividing and organizing into a specific tissue type, for example, cerebral cortex. And with these tiny balls of cerebral cortex, which maybe are about 2 millimeters or so in diameter, 3 millimeters, and we've had them grown up to 1 year. So we're not sure where that limit is and how far we can push them, but so far it's been somewhat common to grow them out for a year or so and still have them be somewhat looking like they're alive. The problem in that field is mostly necrosis, and the fact that these small assemblies that look like cortex don't really have a vasculature or any kind of nutrient delivery system, so we can't grow them out to be larger, old in time, just because there isn't much infrastructure there to support all these cells. But it's a start, and there's a lot of work being done in the field to advance these models, whether it's with artificial scaffolds or literally biologically co-culturing certain capillaries and feeding structures within that tissue. But that's kind of just about the model. My interest is mostly about the electrophysiological properties of these small in vitro organoids and just trying to characterize how they grow over time, if they have changes in neural activity over time, if it's possible to teach them something by stimulating them in certain regions and getting the timing right in between stimulations to perhaps change synaptic plasticity. That's something that we haven't done yet, but we're hoping to do soon. And the most interesting part that we're working up towards is being able to connect a computer to these organoids and be able to perhaps specify some parameters for the computer and have an artificial neural network or some kind of reinforcement learning, deep reinforcement, for example, model, interact with that organoid in order to together produce some kind of targeted behavior that is set by the scientist to be kind of the ultimate goal towards.
Yeah, I think that's definitely the most interesting kind of possibility as well. Like if we're able to train these neurons like with Hebbian learning or something like that, it might be even more complicated, which then would make sense to use some kind of deep reinforcement learning model or just reinforcement learning in general, because this is sort of a unknown environment. But yeah, I think reinforcement learning makes a lot of sense here, just because it's such an unknown environment, but we do have a very good way to measure a reward. For those viewers who don't know about reinforcement learning, I can like talk through real quickly how I think reinforcement learning would work in this context, and then Kate can correct me if necessary.
Sure, that'd be fun.
Basically, reinforcement learning is this machine learning paradigm where you have like an agent and an environment. You don't have explicitly stated training samples like you do with supervised learning, right? In supervised learning, you would show your neural net or whatever machine learning model a picture of a cat, and it would be labeled cat, and a picture of dog, and it would be labeled dog, and it would learn to distinguish them. But with a reinforcement learning model, instead of having these explicitly labeled examples, your agent sort of has to wander around in this environment that you describe. And it gets a reward, which is defined at some part. So maybe you can have an environment, in this example, for example, let's say we want to train this neuron to output a 1, or like when we feed it with like these two signals on the left, and we want it to output a 0 when we feed it with these two signals on the right. Basically, our reinforcement learning agent would interface with this environment of this neuron, and it would receive a positive reward when it succeeds in eliciting that response of a 1 at the right time and that response of a 0 at the right time. And then this machine learning model, right, this reinforcement learning, which is inside this reinforcement learning agent, it'll play around with these neurons a bunch and like keep trying to interface with it and trying different things, right? That's called exploration in a reinforcement learning context. And eventually the theory is that it'll discover a policy which tells it how to feed the neurons in a certain way to cause the outputs to be a different thing. So maybe that was a more neural circuits example, which I think there's much more research on and we're more sure about, but I think a similar kind of context could be applied to like learning how to train these biological neurons, which is a very interesting problem. Yeah, I'm not sure if there's much research on that at all, but that would be super cool if we had this like clear policy for how to feed these neurons certain information or like certain signals in order to train them to do something else. And I think that would not only give us a lot of kind of ability, right? Because now we would be able to create these biological neural nets that could do arbitrary tasks, like whatever we want them to, but it would also reveal a lot about the internal workings of these neurons, like how
Yeah.
these signals get mapped to actual structural changes in the neurons.
Yeah.
Yeah.
I think that's a really awesome way to describe it. I think the key idea is that it might take multiple trials in lots of sequences in order for this reinforcement learning agent to produce the right response in the organoid. And that kind of sequence of events is very interesting. And if we can generalize what sequence of events we need to go through to get an organoid to produce the right action or produce the right output, and that is true across many organoids that we repeat the sequence on, then I think we've tapped into something very fundamental. And that's something that we're hoping to find with this technique of combining neural tissue to computer. We want to be able to generalize some way that we can teach neural tissue, which could ultimately tell us about how neural tissue learns and perhaps what are the biological algorithms that dictate learning and memory. Learning is, I guess, a bit of an ambitious term. I think the humbler term is how do we control plasticity in the organoid? That's the more fundamental question.
Yeah, I've got to say, it is incredibly fascinating to hear about this, especially in the context coming from, talking about reinforcement learning in the deep learning aspect. Where we're talking about those kind of, I guess, maybe non-physical neural networks, and then applying that to these actual physical physical artificial neural networks. That is a really, really interesting way to go. Yeah, and I think it'd be really interesting to see, what exactly that would develop into, especially when you start having that kind of cross compatibility and with computers directly, right? When you're discussing being able to connect with those specific neurons directly. Okay, yeah. So I guess jumping back a little bit, and it was something I kind of wanted to touch on, but we kind of got a little carried away, I think. Jumping back a little bit towards brain-computer interfaces and specifically that recalibration phase. I think that was something that I wanted to bring up as far as Boolepathy goes, and how you guys are addressing that problem, right? Because I think when we consider the subvocalization and its kind of production as an internalized voice, I would imagine that is largely impacted when you consider things, like maybe like an accent or ways people pronounce words differently, or slang, or anything like that, right? Yeah. So how have you guys kind of worked around that, at least? Have you stuck to like one specific person doing all the training, or yeah, I don't know.
Yeah, so last quarter we had multiple sort of like recorders, and that did not end too well, right? Because now we had all this data from different people, and you can sort of think of it in like a deep learning context as like um, everyone's subvocalization patterns is having like a different loss gradient space, right? So you need even if you throw all the data together, right? Everyone's training data, and you just train on that. You're not going to have a set, like you're not going to have a model that learns all of them optimally. You're just going to have a model that learns everyone's suboptimally. So that's sort of the problem that we ran into. That when we were training on one person's data, we would have like 95% accuracy, or like 90% accuracy across trials. So even if they like this wasn't just due to like different locations of electrodes, right? Like we had the person record on one day, and then we would train on that, and then the next day they would put the electrodes back on, and we had like pretty decent accuracy on that, which was kind of surprising because a lot of people report that like even slight perturbations in electrodes do change things. So maybe we're just lucky and they had like perfect placing of electrodes, but I think our model was also just like generalized pretty nicely. But getting back to the main thing, yeah, like when we had different users and we were training across all of those, we saw like with each additional like subject that we added, the accuracy dropped. So when we had one, it was like 90. With two, it was like 75. With like three, it like dropped all the way down to like 65. So we basically discarded this approach of training on all the data at once. And in the future, when we come back to this problem, I think we're going to take something like a calibration approach, where we train some kind of autoencoder to for each individual. So this is sort of how deepfakes work. I actually have not taken the time to think through this, but the basic idea would be to generate to train an autoencoder that can generate a latent space that represents each user's subvocalization patterns. So what an autoencoder does is basically it compresses some information through the encoder, and then it expands it back up in the decoder. It's a neural net, right? So basically, in between, you have this constriction, this low-dimensional constriction, where you sort of force the autoencoder to learn some low-dimensional representation of the data that encapsulates as much of the data as possible. So it's traditionally used in like just compression problems, right? For neural compression, where you want to learn the optimal codec for encoding some kind of data. But at the same time, what you end up having in this constriction is a lower dimension representation of the entire input space. So that what that would and inevitably what that is it's like a symbolic or like semantic representation, because like each of those vectors has to have like a meaning, because that's the only way that an autoencoder can really represent things. And this goes back to like interesting concepts in like the human mind of like how symbols are like generalized symbols are required for humans to understand our environment. If we just represented everything in a high dimensional space, we wouldn't be able to have this interesting kind of understanding. We were actually talking about this like literally yesterday in Ling 258, but like which is like psycholinguistics. But low dimensional representations are very important. And I think autoencoders get to like the core of this problem because they learn these low dimensional representations that have really semantic or symbolic meanings. And in relation, getting back to like the actual main point, is that we would be training these autoencoders to represent each individual's subvocalization patterns. So now we have this small kind of vector that just like from the constriction that represents what their subvocalization patterns are like. And then that sort of becomes our calibrator. So rather than just passing in the user's input into the model alone, we would train the model jointly on both the output from this autoencoder for each individual and their actual subvocalization. And that's like one approach that I sort of thought through for calibration. There could totally be other approaches, like maybe fine tuning or something, but that would definitely be more compute heavy. Actually, I don't know. If you have to train a different autoencoder for every individual, it would probably be more compute heavy, and fine tuning might be better. But yeah, I don't know. I need to think through this more. But there's some very interesting kind of machine learning problems there in terms of how we would go about calibrating.
Yeah, definitely. Yeah, I think you brought up a lot of great points there. Yeah, yeah, and I think going off of that as well too. Yeah, it sounds like you're taking a bit of and God, it sucks too because I was just looking into this for SEAI, and then now it like totally slipped my mind. I believe it's like transitional learning. I believe I'm not sure.
Transfer
But
learning.
it's that same
Transfer.
learning. Thank you. Yeah, where you have that kind of already pre-developed model, and then you start to retrain for a specific kind of stimulus, right? And yeah, I think that'll definitely solve a lot of those problems where you start to run into people who subvocalize differently, which obviously is going to be basically everyone, right? I don't think anyone talks exactly the same. So, yeah, I think that's going to be absolutely fascinating. Um,
Yeah, one thing about like transfer learning, like that thing, like transfer learning as a paradigm has become very common in NLP now, right? We have these huge uh, like BERT, for example. It's just like this huge model that was trained on a bunch of different tasks, and now it just like understands language, whatever that means. And then we use that upstream of like tons of different NLP tasks. We just use like the vector output from BERT to like do some like as our input for whatever other tasks, or we might fine tune BERT to some specific NLP task. Transfer learning is really big there, and I think it's also I it's also very big in the actual brain. I was reading something about this, or I heard something about this a few days ago, that like the language parts of the brain have to be being used for like something else. There was some I literally am not recalling where it was from now, but the basic idea was that like for some reason the parts of the brain that deal with language have to also be dealing with non-linguistic stimuli or non-linguistic computations. um, I'm not sure why, but this reminded me of that, and I will try to remember why and maybe put it in the description of this video if that's a thing. But yeah, sorry.
yeah, no, I think you're totally right as far as transfer learning goes, right? I mean, that digs into a lot about um, like neuroplasticity as far as and that in that context goes for the human mind, right? Where we have a lot of these um, certain tasks, and that it crosses over with a lot of hand-eye coordination tasks, for example, right? Where people who are, let's say, confident in their ability with piano might, um, have that same kind of crossover with hand-eye coordination in other similar tasks, right? And it's that same kind of concept that tends to go across. Yeah, and I think that's definitely something that'll be really interesting um, in the development with Boolepathy, I guess, if that's
I found it. The name of the paper is Pre-trained Transformers as Universal Computation Engines. Basically, it's this idea that uh, transformers trained on linguistic tasks. I think in this one they specifically just use BERT. Um, uh, are good computation engines for all kinds of different tasks. Basically, they freeze the trans. They so like they take BERT. I think it's BERT. Yeah, I'm pretty sure it's BERT. They take it, which is like train, like as I mentioned, it's trained on all different kind of language tasks, and they freeze all the attention layers. So all you have left are these uh, in between you have these like added norm layers, I believe, and you also have these linear layers at the very end. Those are the only things they don't freeze. All the attention heads are frozen, and they find that it has 79% accuracy or something like that for image tasks, for computer vision. This language model gets 79% accuracy for image classification, which is absolutely crazy. And the reason I'm bringing this up is because uh, I was sort of thinking in relation to the language portions of the brain, like maybe like the parts of the brain that deal with language are like all over the place, and maybe I mean I'm not an expert in like neuroscience or whatever, but maybe we're looking at the wrong places, and maybe language is like much more distributed across the different parts of the brain, or maybe the parts of the brain that we do think are explicitly dealing with language um, are just like the tip of the iceberg, or maybe something like that. Oh no.
Yeah, I'm just theorizing, but I'm wondering if there is an innate hierarchical encoding to all kinds of stimuli, whether they're visual or auditory, that might map to similar regions in the brain. I'm just theorizing.
Yeah, exactly. Right. This idea that everything is like hierarchy, everything is recoding. This is what we were talking about in psycholinguistics. That there's this concept called recoding, where it's this idea that in order to represent anything, this like goes back to the autoencoders. In order to represent like any like complex information, when you have a computational like constraint, you have to have these like uh, you have to like re-encode the data in like lower dimensions. Um, so yeah, like maybe like we all know that like language is hierarchical, right? You have like these syntax trees that you build up. But yeah, Kate brings up a very important point that I think maybe there's a fundamentally hierarchical structure of like vision or like the way we see the world itself. And I'm not sure there's been too much thought into how that happens. But like just looking around the room, because yeah, like when you look around the room, it doesn't seem like hierarchical. But I don't know. Maybe it's a hierarchy of classes of things rather than just like locations. I mean, I don't know, but I think regardless, hierarchy is like a very important topic. And since language is so intrinsically hierarchical, uh, I don't think it should come as a surprise that our brain might be using those hierarchical operations to deal with other types of inputs.
Yeah. I think that's that's definitely pretty fascinating. Yeah, and I would say that that's something that I myself would like to look a little more into as well. Yeah. Um, okay, so I think um, I think steering back a little bit more towards brain computer interfaces. We seem to have taken a bit of a brain tangent there. Um, yeah, so I guess um, what would you guys consider to be um, I guess the future of neurotechnology? You know, how far do you think um, it'll be able to advance within our lifetimes, at least? You know, are you expecting cyberpunk type style where there's this there's huge amount of technological integration as far as brain computer interfaces go, or is it still going to be uh, you know left to slowly develop as people are kind of stigmatized, I guess, away from these types of things?
Kate?
I don't know. This is a really interesting question. I kind of have two scenarios in mind, or maybe multiple. One being that perhaps the pace of neurotechnology development will be uh, really fast. Or on the other hand, it could be rather slow, but I think there still would be some innovation and some improvement. And I think a lot of innovation in other areas of technology like electronics or software algorithms, or perhaps neuroscience or understanding bioinformatics and genomics and other things will contribute to the advances in brain computer interfaces, whether they're directly involved or not. So I think even if there isn't much progress in specifically brain computer interfaces, I think our advances in other areas will carry over to that. That being said, I think inevitably neurotech is a really hot area right now, and there are a lot of people that are really interested and working on that front. So I think it's very likely that brain computer interfaces will eventually become more user-friendly and more ergonomic and more widespread, kind of like maybe what we had with VR. Right now, there are lots of VR headsets and applications that you can choose from, and they're starting to get more affordable, whereas maybe 10 years ago, that wasn't really something that was popular or widespread. So possibly brain computer interfaces will have a similar fate, and perhaps at some point everyone will have one, whether it'll be super sophisticated or something like an EEG headset that you put on that looks kind of like earphones maybe. I don't know if everyone will have a Neuralink in the next 10 years or 20 years or so, and whether or not people would, healthy and individuals that don't really need a Neuralink, don't need surgical invasion, whether or not they would choose to get something invasive. I'm saying Neuralink, but I'm not, maybe in the future there'll be multiple companies competing on that front, and that could be exciting.
Yeah, I think one kind of.
That's
Yeah, sorry, go ahead.
good.
Yeah, no, I think one kind of worrying thing of it is how there's so many EEG oriented startups right now, which is like, it's a good thing. I'm happy a lot of people are getting interested in neurotechnology, but I also think it's sort of overselling the hype to investors. For example, like investors will throw money at neurotechnology when like at a company building like EEG headsets without really understanding that EEG is not, it's not Neuralink, like it's not that powerful. It's not going to give you anywhere near the kind of data fidelity that going invasive would. Honestly, all you can really tell with EEG is uh, like EEG spectrum analysis, at least, is like whether someone's paying attention or they're asleep or they're bored, and they're like mind is wandering. That's like, you can also tell some very interesting things. There's like these event related potentials, ERPs, that are specific to certain kind of stimuli. So for example, there's the N400, which I only learned about like a few months ago, but it's a very interesting idea where when you're reading a sentence and you come across a word that you were not expecting to be there, this N400 signal is elevated. So that sort of is like an interesting kind of thing that we can use for like psycholinguistics experiments. But at the same time, you can't build a brain computer interface out of that. Like you can't, like it's not information dense enough to enable you to do something like what Neuralink is claiming that they will be able to do. And again, that's why I think subvocalization has like a lot of unrealized potential, because we already can read these like small vocabularies. It is really a matter of investigating whether it's possible to read arbitrary phonemes from vocal muscles and then chaining those into larger sentences. But yeah, in terms of long-term outlook, I think I pretty much agree with Kate. I think one problem is that with these EEG headsets, I think they might eventually be seen as like quite gimmicky, which could set the field back for a while. Because I know that sort of happened with early VR. Like I know Nintendo released a VR headset in the late '90s, and that sort of caused VR to go under for a while. And VR was supposedly really big in the late '90s. I have no idea, but that's what I've heard, that like it was going to get big, but then Nintendo's headset sort of set it back. So I'm scared something like that might happen with EEG headsets if we have inflated expectations, and the general public has those inflated expectations. But regardless, we need some kind of bridge to go from non-invasive to invasive, and maybe that's EEG, maybe that's some vocalization. Yeah.
I think a lot of progress may be driven by consumer demand, and I'm thinking that perhaps people would be more willing to adopt something non-invasive, and that might be more popular. And maybe eventually people will realize that an invasive headset that is proven to be safe and has been implemented in many other people is very useful and empowering. They might want to consider it too, but I don't think that would be in the near future. I think near future would be non-invasive technologies. I do agree with you that there's a lot more that we can do invasively than we can do non-invasively. I think non-invasively ultimately limits us from being able to look at granular details of the brain. And I think possibly non-invasive will always be more limited than invasive to some degree in terms of freedom to record from different kinds of places and being able to interface with different kinds of neurons. I did hear about some kind of technology being developed where they're using light or beams of light to interact with tissue underneath the skull.
Yeah, like
Possibly,
optoneuronics or something like that. It's
Yeah,
like an entire field of its own now. Yeah.
Yeah, I think I heard about that too as well. Yeah.
Yeah.
I think there's optogenetics, which is where you genetically engineer neurons to be excited by light. And that's more about in vitro experiments where you can afford to genetically engineer something. But in the case of non-genetically engineered neurons, possibly optoneuronics might be the area.
Yeah. Yeah. No, I think I was thinking of optogenetics, but yeah, I haven't heard of that. Then if we can somehow simulate neurons that aren't that aren't even genetically modified. That sounds interesting. Because yeah, that would require nowhere near as much invasivity. Um, because you wouldn't really have to put in these electrodes. You would just have to put in those kinds of what are they called? Those fibers. What are they called? You know what I'm talking about, right? Like the little fibers that they use.
Optical fibers?
Optical fibers, right? You could do it with those, which can go much finer. Like you can have very thin optical fibers. So maybe that's like what they do in research already. But I don't know. Sounds like that could be a better
Yeah,
analogy.
they do implant optical fibers into mice to do optogenetic experiments on certain brain regions. I do think that you can achieve, because an optical fiber is ultimately a tube in which light has to bounce around in order to reach the end eventually. I do think that those will inherently always be thicker than something that's just a wire of metal with an insulation.
Oh wow.
I
Okay.
think you can achieve a single wire of metal to be thinner than a tube
Wouldn't you need
of something that
insulation
reflects
on?
light.
Wouldn't you need insulation on that metal though? Like if you're just sticking it into a brain, wouldn't you need to insulate it somehow? Otherwise, it would start stimulating like random neurons that are all along
Yeah,
the path of the wire.
definitely. So you do need an insulation layer, and only the tip should be exposed where you actually sense and stimulate from. But I don't know. I guess I was thinking that such a construction would always be thinner than um, an optical fiber tube, but maybe they're equal. They could be
Yeah.
made
Okay.
equal.
Yeah, yeah.
Yeah, that's something interesting.
Although one problem with optical fibers though is that they're extremely brittle and you can't bend
Oh.
them. Whereas a wire tube you can bend with a very small radius, and it's very malleable. An optical fiber tends to break a lot, so we would have to engineer some kind of advances in the way we produce these fibrous materials.
Yeah, that's another thing I was going to bring up. Like a lot of the time, hardware seems to be the main bottleneck for brain-computer interfaces and neurotechnology in general. The whole software side has progressed like very quickly. Like it's like actually analyzing those neural signals has improved a lot. Like with EEGNet, for example, in 2017. Since then, like I think the entire field of like neural signal analysis has been migrating more and more over to this deep learning side. But the hardware side is still very much lagging behind, and I don't know if there have been too significant advances on that side for a while. Which I think Neuralink is one of the main things that they're trying to work on is improving the hardware. But yeah, it does seem to be a big bottleneck.
Okay, yeah. So I think for the most part, um, we might be our at our time. Um,
Yeah, I think we wanted to go for an hour, right? We're probably a bit over an hour now.
yeah,
Do we want to talk a bit about the purpose of this podcast and like why we're starting this and whatnot and the inspiration behind it?
yeah, definitely, definitely. Yeah, I think probably the biggest inspiration behind it is kind of which we kind of alluded to a little bit in the beginning of the podcast is um, the lack of podcasts. I'd say in the neurotech field in general, and neurotech in general seems to be a very closely knit and I guess less publicized and um, less media surrounding it. So um, taking into this, uh, taking a first approach into this is going to be, I think, a very interesting thing to go into. And especially when we can take names like the Neurotech Podcast and things like that. Have first dibs on that would be definitely pretty interesting.
Yeah, yeah, you mentioned it like the Neurotech X community. I think they've done a great job. Like it's a very tightly knit community, so I think it'll be very exciting to see what kind of guests we can have on from there because most of them most of the people in the Neurotech X community aren't really researchers. They are more like citizen scientists and people in industry. But I think it shouldn't be too hard to also get like researchers on if we want to go in that direction. So it'll be interesting to have this sort of dialogue between research and industry um, on this podcast over the next few episodes. Um, yeah, I look forward to chatting with some really interesting people on here, and um, yeah, I don't know. Hopefully we're gonna publicize this with the rest of NeurotechX. I think everyone would probably be on board with having like a NeurotechX official podcast. So maybe we'll talk to them and see if like some of their official people want to hop on as well and make this a bit more fancy. But yeah, I don't know, Kate. What do you think? What are you looking forward to most in this?
Yeah, I think I second Alex that it's great to start opening up a discussion about neurotech and having a public forum where people can share ideas or talk about what they're doing and what they're advancing. I think a lot of work that people are doing is not yet published and perhaps could be mentioned informally, and that could really what we think is how dreams are for how we will interface with computers in the future.
Yeah.
A lot of the field does seem sort of secretive. Like, it happens like AI, I think, and like machine learning is publicized a lot, but with neurotechnology, it's definitely a bit more undercover, I feel. So yeah, hopefully we'll be able to publicize this kind of discourse a bit more. So yeah, it'll be fun.
Yeah,
Definitely.
thank you, Alex, for hosting the first session and gathering us all. And it's super exciting, and I think I look forward to many more podcasts in the future.
Yeah,
Same
absolutely.
here.
I think it's been a blast. Yeah, definitely sitting here talking with you guys. Definitely a lot of interesting topics we covered, and yeah, me as well. Yeah, definitely very interested in seeing where this takes off. So yeah, well, thank you guys for dropping by. It was really great talking with everyone. And yeah, I guess we will see where it goes.
Awesome. Thank you so much. See you next week or maybe in 2 weeks. Great, guys.
Yeah.
Yeah,
Okay.
see you. Thanks.
See
Bye.
ya.